let's have a quick chat about the strength of acids and bases. When I was doing calculations on pH, I was telling you things like, this is hydrochloric acid, this is a strong acid. This is perchloric acid, this is a strong acid. What do I mean? It's completely ionized. What do I mean with completely ionized? What do I mean with a strong acid? Well, a strong acid, well, it will be the same case with a strong base, is a substance that when it's dissolving water, it dissociates completely. So before it touches the water, it's a compound, let's say hydrochloric acid. Before it touches the water, the compound HCl is HCl. In the moment it touches the water, it splits completely into hydrogen ions and chloride ions. The same happens with a base like sodium hydroxide, but it is a base. When you have sodium hydroxide, actually the sodium hydroxide is a solid, is the compound sodium hydroxide, NaOH. Interacting, it's an ionic compound into the sodium ions, interact with the OH ions. When you dissolve it in water, you do not have the compound NaOH anymore. What you have is hydroxyl ions and sodium ions. When you dissolve hydrochloric acid, perchloric acid, nitric acid, sulfuric acid in water, you don't have the compound HCl, HNO3. You don't have the compound whatever acid. What you have is hydrogen ions and whichever an ion is that acid. So that's what we mean. And that is what calculations of pH are so straightforward. Because how many moles you have of the acid, how many moles of hydrogen ions they're going to make. And that's it. When you have a weak acid, the things are not that straightforward. A weak acid, to be honest, is like the acids of life, carbonic acid, phosphoric acid, acetic acid, lactic acid, ascorbic acid. The same is true for bases. For example, a weak acid could be hydrogen carbonate or ammonia, sodium hydrogen carbonate or ammonia. When you have a weak acid and you dissolve it in water, most of the compound you have dissolving water will still be the acid. So, acetic acid, when you dissolve it in water, most of the compound you have dissolved in, it will be dissolving water, surrounded by molecules of water, but most of it will be still in the form CH3COOH. The hydrogen, this hydrogen here, which is the one that is going to generate the hydrogen ions, will not have separated. Only a tiny bit will generate hydrogen ions and the corresponding anions. The same is true for bases. When you dissolve ammonia in water, it's like us, when you bubble through water and you get ammonia in water, most of the compound that you have dissolved in water will be the compound NH3, the nitrogen and the 3 hydrogens. And a little bit will generate the NH4 plus and a cation, the ammonium cation, and will liberate OH minus. And that's what we mean a weak acid or a weak base. It means a little bit. Most of it will behave as, that's the compound you've got, and a little bit will be dissociated. It was a bit like what happened with the water. Remember that part of it was ionized, but most of it was as the compound H2O. And that's what we call a weak acid or a weak base. So if you have here this example of the weak acid that we call HA, and only a little, I put a double arrow, or you could put also the 2 arrows. That means it's an equilibrium. It means a little bit of this, the acid is dissociated. Most of it is in as a compound. And some of them will be a tiny little bit, and some of them will be a slightly larger little bit, but it's a small amount in all of them. So how much is a little bit? How can you quantify how much a little bit of, let's say, acetic acid? How much is a little bit of acetic acid dissociated? How can you calculate of a pH of a solution of acetic acid, or predict how many hydrogen ions you're going to have if you don't know what a little bit is? Well, you do know what a little bit is, because that little bit is governed by something called the acidity constant of that acid. And it's specific for each acid and for particular temperatures. So each acid will have a different dissociation constant at a given temperature. And this is how it looks like. The concentration of the hydrogen ions times the concentration of the conjugate base divided by the concentration of the acid that you have dissolved, the weak acid that you have dissolved. And that is the acidity constant for a general acid. You can define something similar for a base and you call it basicity constant. Okay, let's stop 1 second here and look at this equation again, because I'm going to ask you in the next slide to do some exercises on your own. So, an acidity constant is defined by the concentration of the hydrogen ions times the concentration of whichever conjugate base your acid has liberated, divided by the concentration of the acid. And that's called Ka, acidity constant, and the larger that number, that means the numerator, the numbers at the top are larger, that means the more dissociated it is, the stronger it is. So when you have several acidity constants, if you compare the numbers, they will all be weak acids, but some of them will be stronger than others. So if an acidity constant, the larger it is, the more dissociated it will be. It will still be defined as a weak acid because that means it hasn't completely dissociated. If it did, you will not have the acidity constant, but it means, is among the weak acids is a slightly stronger one. So I'm going to ask you to define or to write the two acidity constants for carbonic acid. If you remember from a previous slide, this carbonic acid, H2CO3, is a diprotic acid. It can liberate 2 hydrogen ions, one at a time. So I'm going to ask you to write an expression similar to the one I did in the previous slide for these 2 equations that explain the dissociation of, well, the loss of the 2 hydrogen ions of the carbonic acid. Stop the video now, please. Okay, I hope you stopped the video and had a go at the exercise. Let's try the first one. Okay, the concentration of the products. The first product is H3O plus times the concentration of the other product, the HCO3 minus, the hydrogen carbonate anion. And the square brackets means concentration. And at the bottom, I put the concentration of the acid, and the acid is carbonic acid, H2CO3. And look that the water does not appear in the definition of acidity constant. It's only the acid that you're looking at and the 2 ions it generates. That would be an expression for Ka1. If I write the same one for the second acidity constant, okay, so the second acidity constant, I've got the hydrogen ions, the concentration of hydrogen ions, and the concentration of this species is called carbonate, and divided by the concentration of the weak acid, in this case the hydrogen carbonate anion. So that would be a general expression for both acidity constants for carbonic acid. So the individual values will change and depend, but for a given temperature, these values will stay constant. And these are acidity constants can be measured, are measured experimentally so these are experimental values that you get in the lab, and then with that you can work out if you have a certain amount of carbonic acid, how much will be dissociated, because you know that because you have the acidity constant, and then you will be able to work out, okay, well, if you have this amount of carbonic acid, how many hydrogen ions am I going to get? And that's how you can calculate the pH of a weak acid. The same for a weak base. So if you look at these values, these are experimental values. The first acidity constant is 4.5 10 to the minus 7, and the second one 4.7 10 to the minus 11. So look at how but they are small numbers, 10 to the minus 7, 10 to the minus 11. See how much smaller the second one is. The more hydrogen ions that can be donated, yes, the acid will donate them, but it becomes more difficult. And a large acidity constant means that reaction is easier, as the greater the constant, the greater the strength of the acid, within being a weak acid. The smaller the constant, the weaker the acid is. So carbonic acid is a weak acid. It has two acidity constants. Within the two hydrogen ions that carbonic acid can lose, the first one is much easier to lose than the second one, and so 10 to the minus 7 is larger than 10 to the minus 11. If you want an example of a weak acid that might be familiar to you, acetic acid, which is to be quite common, the acidity constant for acetic acid is 1.8 10 to the minus 5. So I can see, and acetic acid is a weak acid. So as you can see, carbonic acid is quite a weak acid among weak acids, and the second acidity constant is much more difficult. The acidity constant is really, really tiny compared with sort of average normal weak acid.